Okay, so we are going to finish up the Holton synthesis of Taxol. So if you recall, we had started with a ketone here, 27, added a Grignard to get a methyl here, and then used that Burgess reagent to do an E1 reaction and form an alkene. So we're starting from this alkene 29 that is shown here. What we see is in 29 we have an alkene. We're really turning that alkene into a diol. So we're adding two OHs across that double bond. That's done using OSO4, osmium tetroxide. Pretty simple reaction from sophomore organic chemistry. Next, in the next couple steps, starting from 30, we're really going to be working on forming the D ring, right? Forming this D ring here. This chemistry is not that difficult because we can take advantage of the fact that we have a primary alcohol, a secondary alcohol, and a tertiary alcohol, and we can react these at different times. So the first step here is to protect the primary alcohol. Okay, that's going to be kind of a protecting group that we don't need on there for a long time. So they're going to use TMSCl and triethylamine. TMSCl and triethylamine. So that will add a trimethylsilyl group to the primary alcohol, getting you compound 31. From 31 to 32, they're now going to add a group to the secondary alcohol, and we really want to turn that secondary alcohol into a good leaving group. So the way this was done is they used a base here, LDA, sort of a strong base to use for an alcohol, but probably because it's hindered. So, and then also probably just preventing that you don't deprotonate the tertiary alcohol. You can selectively deprotonate the secondary alcohol. So LDA and then Taxol chloride, TSCl, right? So just remember with our Taxol chloride group, right, that's toluene sulfonyl chloride, right, S double bond O Cl. So that's our Taxol chloride, TSCl. That adds, the OH becomes an O-TOS group. Okay, so that's a really good leaving group that turns the O into a very good leaving group, giving you compound 32. All right. Next, what they're going to do is essentially what we're trying to get is this primary alcohol to do an SN2 attack and kick out that Taxol group. So step one is really deprotecting that silyl group, right? We mentioned that that was going to be on very quickly. So a little bit of acid, acetic acid, can deprotect, remove that silyl group, giving you back your primary alcohol. And now really what we're looking for is this primary alcohol, right, to attack this carbon here, kicking out our O-TOS as a leaving group. And they do that by actually adding a base, DBU. So DBU is a good nitrogen base that'll deprotonate that hydrogen, allowing it to the alkoxide, the O-, to do the SN2 attack. All right, so let me just give you the structure of DBU. This is the first time we've seen this. It's a pretty good base. So DBU is actually a fused ring system with a 6-membered ring and a 7-membered ring. Let's count those: 1, 2, 3, 4, 5, 6, 7. So that is a 6-membered ring and a 7-membered ring. Make that a little bit clearer for us to see. And this is just a really good, good base to deprotonate alcohols. So DBU will deprotonate this hydrogen, allow that to attack. We've now formed the D ring here, so that is compound 34. Okay, synthesized 34. 34 to 35 is quite simple. Just need to protect that tertiary alcohol as an acetate. We know how to do this. Acetic anhydride, AC2O. Pyridine is the solvent. And they add a little bit of DMAP, right, to make that protection go quite easily. Looking at 35 to 36, right, we've deprotected our test group, our triethylsilyl group. Okay, two real ways to do that, TBAF or HF pyridine. So here they used HF and pyridine to remove that silyl protecting group. All right, they were able to selectively remove the test group, but not the TBS group. Okay, so probably had to be a little careful with this reaction, but remember the triethyl is smaller, easier to deprotect than the tert-butyl dimethylsilyl. All right, so HF pyridine can selectively remove that test group. Now we're kind of looking into the similar chemistry that Nicolau did. We have this carbonate group that needs to be opened up, right? So I think that was done the same way that Nicolau did. So using phenolithium, right? Phenolithium basically, right? It's basically like a C minus. That's going to attack the carbon of the carbonyl, form the O minus, and then break down and break that bond here. So you're cleaving that bond, getting your free OH there. So phenolithium, same chemistry that Nicolau did, right? Adds that benzoyl group, BZ. So if you have an OBZ, or that's O, C double bond OPH. All right, just a reminder about the abbreviation BZ. 37 to 38, right? We've got this alcohol that was just recently deprotected. We need to oxidize that. Hundreds of different ways to do the oxidation. Here they used TPAP-NMO. So that was the oxidizing reagent to turn that into a ketone. 38 to 39 is kind of an interesting reaction here. I wouldn't say this is something super common. It's sort of a specialized reaction here that worked well. So we're not going to go into a great amount of detail on it, but they use potassium T-butoxide and then benzene selenic anhydride. Benzene selenic anhydride. And essentially what that did is add an OH to the alpha position and then flip the oxidation of the new O that was added. So again, this is sort of a specialized reaction that worked well here. I'm not going to go into too much detail on it just to save time. It's not something that's really super common, but that allowed the molecule to be oxidized in the way they needed it to be oxidized. Right, we've got that free secondary alcohol. Again, we need to protect that as an acetate, acetic anhydride, pyridine, and DMAP. Again, very simple to protect that alcohol to give us compound 40. Okay, almost done here. Pretty straightforward. Compound 40, need to deprotect that TBS group. Again, TBAF or HF pyridine. They used HF pyridine here. Probably had to heat it or react it a little bit longer than they did with the test group, but not difficult to remove at all. That gets you the free alcohol, okay? And then, just like we saw before, same thing with the Nicolau synthesis. We're adding on this tail with this lactam group, right? There's our lactam group. They do that by adding the lactam, and then you need a good base. So lithium HMDS, lithium hexamethyl disilazide. So that is a very strong base, lithium to a nitrogen to two silyl groups. Okay, so this is a really strong base. What we have to remember here is that is deprotonating this hydrogen here, turning that into an O minus, and we are attacking the carbon of the carbonyl, right? So our nucleophile attacks the carbon of the carbonyl of an amide, right? Amides are not great electrophiles, so you have to have a really, really strong base to do this. Okay, so here is the new bond here, right? And then essentially what they've done here is they've cleaved that carbon-nitrogen bond. So we kind of number these appropriately. 1, 2, 3, 4 to the nitrogen. 1, 2, 3, 4 to the nitrogen. And just notice the stereochemistry here is maintained. So if you kind of flip or rotate these around, you can see you get the same stereochemistry, right? The stereochemistry is determined here by those groups, and that is maintained. It's just drawn a little bit differently in this molecule. So that gets us to 43, right? We've now added on the tail of the compound. 43 to 44, removing that test group. Again, this is HF and pyridine. Great way to remove the silyl protecting groups. Nothing new there. And then the last reaction here is removing the bomb group, right? What's great about the bomb group as an acetal is that can simply be done using H2, right? Hydrogenolysis, H2 palladium on carbon. That removes that bomb group, and then you are left with Taxol, all right? And the Holton synthesis is done, all right? So kind of common chemistry we've seen before, just to finish off the synthesis, nothing really new. The only thing really unique is this 38 to 39, but that's not really a big focus for us. So we're just kind of following the same chemistry and reactions that we've learned before.